what do we mean by nanomaterials? So if we can consider the size, then size should be less than 100 nanometer, at least in one dimension. If we consider any material, if size should be less than 100 nanometer, at least in one dimension, then you can say that is a nanomaterial. But what is the importance of nanomaterials? Since these nanomaterials have high surface to volume ratio or quantum confinement effect, we can use those nanomaterials for several applications. If first I consider the gas sensing application, for particular a gas sensing application, generally selectivity and sensitivity, both things plays important role. Does nanomaterials have higher selectivity compared to the micro or millimeter materials? If that question comes in our mind, the first I'll give a basic example which was related to us. From that understanding, we can get a knowledge that yes, nanomaterials have higher selectivity compared to micro or millimeter materials. You can see here in my first slide that I put here two babies. One baby of around 5 months, another baby or another child is around 5 years old child. So one is 5-month baby, another is 5 years old child. So in front of them, I put their family members. Then I told both of them, that 5 years old child and the 5-month baby, to select any one from their family members. So if we told to select anyone from their family members, particularly if we consider the 5 years old child, so what will happen to whom he will select? He may select to his mother. At the same time, since he knows everyone, like his mother, like his father, grandmother, sister, or so in his mind, maybe 70% selection will come towards his mother. At the same time, also another 30% will be towards to his father or brother or sister. So means selectivity, in terms of selectivity, we can understand the selectivity will be 70% for the particular, for the 5 years old child. But what will happen when we will tell that 5-month baby to select any of one from their family members? I'm sure he or she will only come towards to his or her mother. Means he will select or she will select only to his or her mother. Means the selectivity in this case, particularly in this case, will be 100% towards his or her mother. So now if you can consider the size of between them, obviously the 5-month baby has smaller size. So from this basic example, we can understand that if we can reduce the size of a material, then the selectivity will increases, which plays an important role for particularly for gas sensing applications. And another way, breath, from the literature we found, the breath is an indication of human health condition. In our breath, we are always releasing several gases like acetone, ammonia, ethanol, hydrogen, carbon dioxide, or carbon monoxide. And we found from the literature, if someone can detect a very particular amount from our breath, then you can say what the patient is. Like if in our breath from certain percentage, higher amount of acetone is detected, then you can say that patient is a diabetic patient. If in our breath, like ammonia will be detected, then you can say from the certain percentage, if higher will be detected, then you can say that is a renal disease person. If nitric oxide will be detected, then you can say that is a asthma patient. If hydrogen will be detected, then you can say that is a lung cancer. But to detect those amount, you can know that for a diabetic patient, if we go to the medical, then he has to do several tests. So means the cost becomes very high because they have to do like some gas chromatograph. So there are several techniques are there which are expensive, most expensive, and also several ways they have to do, perform. So still yet, there are on the other way, like those are the volatile organic compounds which can be detected by using gas sensors like metal oxide based gas sensors. But still yet, there are no such sensors, no such gas sensors are available in the market, like low cost gas sensors are available in the market which can detect trace amount of the several gases. So we think, why not we will prepare some low cost or cost effective materials which can detect those particular amount of those volatile organic compounds from our breath, or we can use as a breath analyzer. So generally from the literature we found that transition metal oxide plays an important role in these areas. Mainly tungsten oxide, tin oxide, those are very good materials is used as gas sensing application, used for gas sensing applications. To enhance the performance of those materials, they generally, people what they did, generally they use some noble metals like gold, platinum, palladium, silver. They decorate their materials on those transition metal oxides, on those like the tungsten oxide, the tin oxide, they decorated those or they engineered those materials by using some noble metals. Then their performance was increased. At the same time, cost of the device also increases. So it is important to prepare the material at low cost. So our first objective comes to prepare some hierarchical nanostructures which can detect the volatile organic compounds from our breath, and as we can use as breath analysis. We take here tungsten oxide, tin oxide, and we prepare this material in a simple way, only in a one pot synthesis methods. We prepare this material, and we found this material highly important to detect those several gases. Also, we reported for the first time these materials. How we prepare these materials, we generally take some precursor of those materials and we edit, and we use hydrothermal method to prepare this. Only tungsten oxide we prepared, only tin oxide we prepared. Then we just vary the tin precursors and we prepare the composite of tin oxide and tungsten oxide. So after this preparation of any material, when we prepare, then our aim is we have to characterize that material, what the material is. So to understand the structural property of a particular material, if we want to know that what the material is, the fingerprint of a material, to understand the structural properties, like to understand the phase of the material or to understand the crystal structure of the material, we have to perform X-ray diffraction. From powder X-ray diffraction, we can understand what is the phase of the material or what is the compound is. Then to understand the optical properties of the material like band gap or optical absorption, we have to do UV visible technique, where we can understand the optical properties of that material, of that particular material. To understand the size, shape of particular material, we have to do ACM or FEACM, like field emission scanning electron microscope, or we can also from transmission electron microscope, we can understand what the morphology or microstructure of a particular material, where we can calculate the size or shape of a material. Then to understand the surface area of a material, we have to do BET surface area. So that material we prepared, like tungsten oxide and tin oxide, what the material we prepared, we first check what the size of the material, what is the morphology of those nanostructures. You can see the first one, the first in the figure, if you see image in the first figure, that was only WO3, only tungsten oxide. But you can see that from that figure, we can understand those are flower-like shapes, flower-like hierarchical flowers. And those flowers consisting or composed with several nanoplates. You can see on that insert, that is the high magnified image, and where you can see those nanoplates are clear surface. Then we prepared only tin oxide, where in figure B, where we got only nanoparticles. And we found the size are around 5 to 10 nanometer. And when we prepared composite by varying this tin precursor during the synthesis of that composite, we take one material, we prepared one nanomaterial by very less amount of this tin precursor. Another material we prepared by moderate amount of that tin precursor. Another material we prepared with a high amount of tin precursor. And that also things, whatever we prepared, that was reflected also in our FES images. You can see from the figure C that in that you can see the high magnified, on that high magnified image, very teeny bright particles are decorated on that plane surface of the tungsten oxide nanoplates. And when we can see also those nanoparticle size are very small. When we little bit more amount of tin precursor we add during the preparation of this composite, you can see that moderate amount of, like some little bit higher amount of these tin particles are decorated over the nanoplates. On that inside image, you can see that the concentration of tin particles, tin oxide particles also higher. And when we put some higher amount of these tin particles or higher amount of tin precursor, then you can see that agglomerated tin oxide particles are decorated on the plates. So that things also reflected in our, like to understand in a material, when we prepared some materials to understand the elemental composition, what are the elements present on that particular material, we have to do NRT dispersive X-ray spectroscopy or EDS analysis. So from that EDS analysis, you can see that also that tin precursor, when we varied, then the element, the atomic weight percentage of tin also changes. You can see for higher amount of tin, you can see the higher amount of tin, because the higher amount of tin elements are there, tin atomic percentage are there. In moderate also, moderate amount of atomic percentage, atomic weight percentage are there. Similarly, only tungsten oxide, there is no peak of tin. Similarly, only tin oxide, there is no peak of tungsten. And particular this paper, recently already it was cited 115. So more than 100 citation already done with this particular for this paper. So after this one, so whether to further character, to further understand about that morphology or the microstructure, we again did the TM analysis. From the TM analysis, we also found that only tungsten oxide, those are nanoplates. Only tin oxide, those are particles, a size around 5 to 10 nanometers. And when we prepare some composite, you can see that on that place, those particles are decorated. So from that TM analysis with the transmission electron microscope, we can understand that these are correlated with our FESM results. The difference between FESM and TM, that in FESM, that is a 3-dimensional image we'll get, and in TM we got 2-dimensional images. So to understand whether this one is tungsten oxide, tin oxide, or only tungsten oxide or only tin oxide, to understand this as phase, to understand the crystal structure, we did X-ray diffraction. You can see from that XRD spectrum, from this XRD spectrum, we perform all the samples. We found from that the first one, only tungsten oxide, it was matches with the tungsten oxide. Only tin oxide, that sample we prepared, we got tin oxide. However, when we varies the tin precursor, we did not observe any extra peak in the tungsten oxide plates, any extra peaks for tin oxide. But on the other way, but the intensity, if we can see the intensity was increases, which suggests that crystallinity increases when we incorporate the tin oxide, the tin precursor into that sample. But there is no, on the composite sample, we do not found any tin oxide peak. This is maybe attributed to that very less amount of, since we use very less amount of tin precursors, so we did not observe any peak. But to understand the chemical state or oxidation state of a sample, of any sample, we have to do X-ray photoelectron spectroscopy. From that, we can understand what is the chemical state of the material. or oxidation state of a material. Also, we can understand the chemical composition of a material. So from this XPS or X-ray photoelectron spectroscopy, we can see that on the surface spectra, you can understand that yes, both tin, tungsten and oxygen all are present. But from this oxygen peak, we can, and also from this tin peak, we can understand that this is SnO2, not Sn. So from that XPS analysis, we understand that this composite was tungsten oxide, tin oxide, not tungsten oxide, tin composite. So after we successfully prepare these nanomaterials, these nanostructure materials, then we use these nanostructure materials for gas sensing applications. And we found, particularly we found these materials are highly selective and also those are temperature dependent. We found, we tested for all the 6 samples we tested for ethanol, for ammonia, for ethanol, for acetone, which are primary biomarkers. We found particularly one sample when we uses some high amount of tin precursor, that is, this was highly selected and this was highly sensing towards ammonium at a temperature 200 degrees centigrade. And when we use a moderate amount of tin precursor, we found at 300 degrees centigrade, it was highly selective towards ethanol. And we found for only tin oxide, it was highly selected for acetone. And also to understand the selectivity, sensitivity, we also tested several other gases, whether this was only particularly selective for this one or for other gases also. You can see that from the selectivity also, we found the high amount of tungsten oxide was highly selected for ammonia, and the moderate amount of tin precursor was high, their composite was highly selected for ethanol, and only tin oxide highly selected for acetone. Now, if we can tell that this shows the high concentration of tin oxide precursor, tin precursor shows towards ammonia, and this one towards ethanol and acetone. If without science we can present, then it will be not acceptable. So to publish a good paper, the important is that what is the science behind it, we have to find out. Why particularly high amount of, when we use high amount of tin precursor, it was highly selected towards ammonia. By moderate amount of tin precursor, is highly selected towards ethanol. By only tin oxide, is highly selected towards acetone. So generally when we prepare some heterojunctions, like we take tungsten oxide and we take tin oxide, means there is a heterojunctions between tungsten oxide and there is a depletion region also between the tin oxide and tungsten oxide. So more number of tin oxides should be there, then more number of junctions will be there, more number of active sites will be there. So what will happen? We found that kinetic diameter of those molecules like ammonia, ethanol, and acetone. We found the kinetic diameter of ammonia molecule is the smallest one, that is 0.26 nanometer. However, for ethanol, that is 0.45 nanometer. For acetone, that is 0.47 nanometer. So since the kinetic diameter of this particular ammonia molecule is very small, and particularly here when we have taken a high amount of tin precursors, means more number of junctions will be there. Also from this FESM image, we found that agglomerated tin oxide particles decorated on the plates. So since more number of junctions will be there, more number of active sites will be there. So there is a chances that since the ammonia molecule is smaller in size, so it can interact with each junction, so that we can able to get high selectivity for ammonia, for particularly for high amount when high amount of tin precursors are there. But in case of ethanol, since that ethanol, the kinetic diameter of ethanol is 0.45, little bit larger, so it cannot interact all the junctions for high amount when high amount of the tin oxide particles will be there, or in agglomerated case. So we cannot get high efficiency or high selectivity for the highest amount of the tin oxide particles. But in case of moderate amount, it is able to interact with all the junctions, so we will get higher amount of the selectivity for ethanol 1 at moderate concentration of tin precursor on that W3 tin oxide composite. And for tin oxide case, we found that particle size plays important role. Since the particle size of this tin oxide are very small, like 5 to 10 nanometer, so means according to the rule, we know that in general, we know that if it Debye length, if it will be twice of the Debye length, like the tin oxide particle, the length is 5. So if it will be twice, then it can interact the maximum number of oxygen molecules from the air atmosphere. That's why for tin oxide case, we will get high amount of selectivity for acetone at higher temperature. So from this, we understand that material we prepared in a single process, and we do not use any noble metal free. We prepare this nanostructures materials, and we found those materials are highly selective towards several gases or biomarkers, towards acetone, ethanol, and ammonia. And we calculated also LOD and all those things, and we found that we can use also this one for breath analysis. And particularly this material also, we also given a table on that particular table also we mentioned, and we found that our result was higher 10 times, 20 times higher compared to the not only the pristine one, but also compared with noble metal oxide or noble metal composites. So here we can understand that the performance of the towards ethanol or towards ammonia, it was the composite shows higher performance compared to the pristine or pure W3 or pure SNO2. So here we engineer the nanostructures of tungsten oxide and tin oxide. We engineer those two towards to prepare a hybrid or heterostructures which shows higher performance towards the gas sensing applications. So now also we engineered also nanostructures for other applications, the same one, but we prepared with some platinum, and we found those are very good materials for fuel cell applications. So now how our environment being polluted. Now I want to discuss about the environmental pollution and their remediation. So how environment being polluted? If we think about the pollution, how many types of pollutions are there? Generally, air pollution, land pollution, sound pollution. And another one, the most major biggest environmental threat, that is water pollution. Since water content is 75% in the worldwide. So what is the major source for water pollution? In general, the wastewater discharged from the industries or commercial bodies. Generally, people are using like paint industry, ink industry, where we are using some different colors of the t-shirts or saris. They are using generally dyes and generally colors. So they discharge those wastewater to the rivers, towards the rivers or towards the ground. And those wastewaters, those colorful waters, those are not only harmful for environment, but also harmful for aquatic life, since it blockages the sun rays. Hence, those dyes we can say like methylene blue, rhodamine B, rhodamine, or several dyes are there. I just given some examples of methylene blue, rhodamine B. And another most emerging pollutants we can say that heavy metals like chromium, that is also one of the biggest environmental threat. The chromium 6. Chromium, it has two oxidation states. One is chromium 3, another is chromium 6. Chromium, that hexavalent chromium, that is highly toxic, carcinogenic, and the presence of this hexavalent chromium in the groundwater also in Odisha, several places are there. There also in the groundwater, the presence of chromium 6 are there. The presence of this chromium 6 in groundwater, it causes skin cancer or kidney damages. and several other diseases also due to the hexavalent chromium, due to the chromic inhalation by the drinking water. So it is important to discharge to detoxification of these chromium 6 or reduction of this chromium 6. On the other hand, chromium 3, it is a human nutrient. It can be readily precipitated out as chromium hydroxide. So I will discuss all in detail. So how we can remediate, what are the remediation technologies are there, how we can remediate those environmental biggest threats or water pollution like those dyes or those heavy metals from the wastewater. There are several techniques are there, several technologies are there. One is physical treatment, that is adsorption process. This adsorption process, this is a simple way that the large concentration of dye can be directly adsorbed on the metal surfaces or on the material surfaces. But here, in a very short time, we can degrade high amount of high concentration of dyes. And biological treatment, another is biological treatment. I will not emphasize on that biological treatment or microbial reduction. That is a little bit lengthy process. And chemical methods like catalysis or photocatalysis. That is an interesting topic, interesting one. So photocatalysis, nothing but photosynthesis. Everybody know about photosynthesis. So what will happen in case of photosynthesis? In general, in photosynthesis, like chlorophyll, the presence of sunlight and water, the chlorophyll break down carbon dioxide into oxygen and glucose. So here similarly, in case of photocatalysis, generally for photocatalysis, generally we use semiconductor materials. Semiconductor means it has some band gap, like conduction band will be there, valency band will be there. Generally for the photocatalyst should be semiconductor materials. And here that photocatalyst, that semiconductor materials, that photocatalyst, in the presence of light, like photosynthesis, the presence of light, these photocatalysts degrade those hazardous organic dyes to ideally carbon dioxide and water. So what will happen? You can see here, this is a semiconductor, this is a semiconductor material which have valency band and conduction band. So when we will apply light or sun, if the band gap of this one is higher compared to the material band gap, then what will happen? Electrons will go to higher energy state from the valency band to conduction band. So when electrons will go to higher energy state, the absence of electron is nothing but hole. So hole will be there. And these react with air atmosphere. So when it will react with air atmosphere, then radical formation will occur. Are these S plus radicals or O2 minus radicals or OS radicals? Those radicals when interact with some organic dyes, those are not only harmful for environment but also for aquatic lives. They converted ideally carbon dioxide and water. That is the basic of a photocatalysis technology. And another way, electrocatalysis or photoelectrochemical water splitting. On that, we can split water into hydrogen and oxygen. So what will happen? This one I will explain in detail on that also, but here what will happen? So when in a similar way, when we apply some potential, then similar way, the electrons, there will be some anode and cathode, and that electrons will react with it waste, and we will get some H2 gases, hydrogen gases. So why hydrogen is important? In general, about this electrocatalysis or photoelectrochemical water splitting technology. But so our aim is we have to generate more number of electrons and holes. But if those are recombined, then heat will generate, so nothing will happen. So we do not, our aim is not to recombine both electrons and holes. Why hydrogen is important? Now, from the worldwide annually, 44.5 million tons hydrogen was annually produced. Where we use this hydrogen? we are generally using those hydrogen gases for industrial purpose, like for cement industry or for ammonia, like for fertilizer industries. There we are using these or other chemicals also, we are using those hydrogen gases. So these hydrogens, how we can produce these hydrogens? Generally, there are three basic ways where you can produce this hydrogen. You can see now in this case, here, there are three basic ways where you can produce these hydrogens. First one is like steam methane reforming. We can produce hydrogen from that technology. Or you can also use coal gasification, and another is water electrolysis. Still now, 95% of hydrogen, that 44.5 million tons hydrogen, whatever they're producing annually in the worldwide, still now 95% hydrogen was produced by using this first two technology, using steam methane reforming or coal gasification. Only 5% are used water electrolysis technology. If we can see the first two technology, steam methane reforming or coal gasification, you can see what we are using, how we can produce this hydrogen. You can see in the first cases we are using methane, and also you can see on that reaction our outproduct byproduct is carbon dioxide. That methane, that is a fossil fuel, means we are using, means we are depletion of fossil fuel occurs. And in the second case we are using coal. Also in the output you can see that where output is carbon dioxide, where carbon dioxide releases. In the first two technology, carbon dioxide releases, means our environment pollution occurs. At the same time also we are using our fossil fuels. So depletion of fossil fuels, and also where environmental pollution we are creating. Thus, it is highly important for the researchers to explore sustainable, clean environmental fuel like hydrogen in a sustainable way we can produce. If you can see the third one, water electrolysis. We know that water, one of the biggest, like 75% water in the world, where 75% of water is there. So you can see the primary source for water electrolysis is water. And if we do the reactions, you can see now here is we will get two hydrogen and oxygen. There is no carbon dioxide, means that is a clean technology, a sustainable technology, or you can say green technology, where no emission of carbon dioxide occurs to produce hydrogen. But why people not tried with this one previously? Why so much research have not done still yet about this hydrogen generation? The problem is that in the industry problem is that here to split water, we need some catalyst. That material, whatever we are using, that material, mainly noble metals are used, is platinum. That is the benchmark material where you can produce the highest amount of hydrogen. So if we use the platinum, then the cost again becomes higher. So this technology, so that's why, so our aim is to implement or to prepare some of the metal oxides or metals where the without noble metals we can prepare this we can prepare for hydrogen generation. Low cost material, cost effective materials. It is highly important to explore cost effective materials where you can produce hydrogen. So now the size plays important role. Previously I already, for the sensitivity case, for the selectivity case, we understand that size plays an important role. Also for this environmental pollute, for this water treatment, wastewater treatment, does size plays important role. If we reduce the size, what will happen? You can see that if we reduce the size, the first thing is that our surface to volume ratio increases. So here you can see we have taken a basic example. One big box, each side is 3 centimeter. So if on that cube, each side will be 3 centimeter. So what will be the surface area? Surface area means length into breadth. So 3 into 3 is 9. It has 6 faces, so 54. If we come to the second one, just the smaller one, the size is 2 centimeter, each side is 2 centimeter. Then what will be the area? 2 into 2 is 4. Then It's 6 faces, so 6 into 4, 24. What will be the volume for the first case? Since the side is 3 centimeter, length, breadth, and height, so 27 will be the volume. So if we measure the ratio of surface area is to volume, then we will get 2:1. And second case, if similarly we calculate for 2 centimeter, we will get 3:1. If each side will be 1 centimeter, what will be the surface area? Since 1 into 1 is 1, 6 faces 6, and volume will be 1. So surface area to volume ratio is 6:1. You can see from this example, if we reduce the size of a material, then its surface to volume ratio increases. So that is the beauty of a nanomaterials. If we can reduce the size, then the surface to volume ratio increases. Another basic example I can take. Suppose I will tell all of you to prepare a curry. If you prepare a curry, suppose 100 gram green chili I given to you to prepare a curry, 100 gram green chili you use to prepare one curry. So without cutting that green chili, you use the green chili and you prepare a curry. The same 100 gram green chili I given, again you just prepared another curry by cutting 2 pieces. And one more curry you just prepared with the same amount of this green chili by grinding, by preparing a juice of that green chili, and you prepared a curry. So where you will feel more chillness. The amount is same 100 gram for all cases, but obviously you will find higher when you prepare a grind, when you prepare a juice of that green chili. So what exactly we did? We exactly reduce the size of that green chili. When you reduce the size, you prepare a juice, then we found more chillness will occur. Means that the surface reactivity increases to the tongue, towards the tongue. So from that example, you can understand if we can reduce the size of a material, then it will be highly reactive, or the reaction sites increases, or active sites increases. So also crystal phase plays an important role also for the environmental applications. So so we prepared several metals, several materials, and this particular material, we did not use anything. We prepared in a simple way, and just we take a picker and we use those precursors. Means anybody can prepare this material without any stirring, without, like we just stir it, but without any furnace. All these things we prepared at room temperature, and also we reported for the first time this one we prepared at room temperature. And you can see that we just taken some sodium tungsten precursor in water, and we just add a HCl, and we got some product, and we found that is tungsten hydroxide. To tune the nanostructures, to engineer those nanostructures, we again use some oxalic acid. So because first we check that how the reaction will occur, and then we think that okay, we use a size controlling or shape controlling reagent as oxalic acid. And when we use that one, you can see now again that becomes transparent, the solution becomes transparent. Also again after 1 hour or 2 hours, again we found this one. So everybody can do this experiment, and we prepare some powders. Then we check those samples, the morphology, the size we check. We found when we prepared only by adding those things. You can see here, these are the FASM images, AB are the FASM images, and these inserts are the sample powder colors. And we found this, you can see that those plates, those nano plates, those plates are higher, bigger in size. You can see now bigger in size, around 400 to 600 nanometers, and also irregular shape. When we use oxalic acid, you can see now the size was decreases around 40 nanometer to 100 nanometer. Size decreases, and also you can see that plates are very regular shape, a square shape. And we just heated the samples and we prepared some tungsten oxide. Then further to understand the crystal structure or to understand the phase analysis, we just did the X-ray diffraction of those samples. We found that different phases, we found different phases and different materials was prepared by using this oxalic acid. When we just use oxalic acid, it was not controlling on the at room temperature, it was not controlling the size, but also it was controlling the phase. So we found W3H2, W32H2, and when we heated both the samples, then all converted to W3. To understand the optical properties of those materials, because the important for photocatalysis application, generally band gap plays an important role. Why? In general way, for photocatalysis, generally the high larger, generally previously generally the KIO2, SNO2, ZNO, those are very good material, well-known material for photocatalysis. But their band gap is higher than 3 electron volt. If band gap is higher than 3 electron volt, means it's the wavelength comes towards the UV region or ultraviolet region. But from the sun to earth surface, only 5% are UV rays, rest are visible rays. Hence, it is highly important to design the material so band gap should be in the visible region so that we can use the maximum percent of the sunlight. So we calculated the band gaps and we found all the band gaps less than 2.5 electron volt. So we can say that we can use these materials in under visible light. I already told that chromium 6. So what are the sources of chromium 6? The sources mainly like from textile industries or from cement industries, metal finishing, chrome plating. Those are the sources where chromium 6 is developed. You can see now we use those materials for the chromium 6 reduction, and we found that you can see the first in this plot figure A. The first one is the chromium. When chromium 6 was present, the color becomes yellow. After certain time, when we expose to the light, after certain time, around 60 minutes, you can see we are getting a colorless liquid. It's like water. So from that means by visualizing this we can say that the color changes, means we can say that chromium 6 reduction will occur. But for practically to understand this, we did UV visible spectroscopy, and we found that observance was the concentration observance was decreases. And particularly we found that the smaller size material and smaller band gap material shows higher activity compared to the other materials, compared to the bigger size materials. So here also we found, so you can see now that when that oxalic acid where we used that material, the W32H2, where we found the maximum, that we found that efficiency is 96%, which is higher compared to the other materials. So this is due to the lower band gap, smaller size, and also higher specific surface area or effective surface area. Further, the same material, we apply this one as a bifunctional way. We apply this one for adjustment technology for the methyl blue dye. You can see from the figure A, you can see that from the first one on the inside, this is a methyl blue dye with a high concentration methyl blue dye. When we put our material inside this one, within 1 minute we get a colorless liquid. So within 1 minute, it degrades that chromium 6. Also, same thing was represented in UV visible graph also. And we test for all the samples. We tested with the various concentration, and we found also similar way. We found also the smaller size material W32H2 shows higher performance compared to the W3H2 or W3. So for practical application, it is important that durability or stability plays an important role. We also did for several cycles, around 15 cycles, and we found it was highly stable. But you can see on that also the first cases, it was shows around 96%, but second cases it decreases. Why? Since we are using adsorption technology, not photocatalysis here, we are using adsorption technology, means we will not use any light, we just put the material into that concentrated dye, and after certain time, all the dye molecule will adsorb on that metal oxide surfaces. But how we can again, we can collect our material. So for that purpose, we have to heat that material. So when we calcine, we heat the sample for 300 degrees centigrade. Then since the previous one was tungsten hydroxide, so when we heat it, it converted to oxide, water molecules will goes away, so it convert to oxide. So that's why after the first cycle, it will be converted to oxide, so its performance will be decreases. After that, it was stable. So we prepare several metal oxides, metal oxides, metal sulfides for the wastewater treatment for different dyes. You can see we just here in this case, similarly we prepare some indium samples and we use like some RSB, rhodamine B dye, ARS dye, and we found it was highly effective also towards those dyes. Similarly, in another, we prepare some other nanostructures. You can see that we engineer here nanostructures with different morphology, like some here you can see that though all are nanoflowers, these are indium sulfide samples. Those all are flowers. But in the last one, you can see this looks like brick shape, and this is hollow shape, and in this case there is no hollow. So similar way, we engineer those nanostructures, and we found that when the surface area is higher, then we found the activity was higher. This one also we tested for methylene blue dye and crystal violet dyes, two different dyes. And for this one, I think we tested under just a bulb, 100 watt, 250 watt bulb. After we preparation this material, we just use some 250 watt bulb and we expose this 250 watt bulb to our dye solution including our materials, and we found after certain time, 30 minutes or 40 minutes, we found the materials completely degrade those dyes. And this work we did with the collaboration of KIT University. Recently, I think we published. And here also they prepared, the sample was prepared at KIT University, and then we tested, I tested here. And here also they prepared some like multiferroic materials, like some strontium cobalt co-dope. You can see they also engineer in KIT University, they also prepared bismuth ferrite. Then they engineered this in the case A, you can see those particles have larger size. So they engineer this one, they dope from A side and B side, they co-dope with strontium and cobalt. So when they dope with two strontium and cobalt, you can see the particle size was reduced. So when the particle size was reduced, then it was like shows higher performance compared to the pristine or pure BFO. So now towards hydrogen generation, as you understand, it is highly important to develop some noble metal-free materials which can able to achieve higher hydrogen efficiency. We prepared also in a simple way, we prepared tungsten hydroxide and oxide. You can see now here, similarly, we never use anything. We take some, when I did this material, I first checked that how it will be soluble, the WCl6. So I found that it will be soluble in ethanol, not in water, it is soluble in ethanol. So I just checked by using this one. As previously they told, I found on that on that packet, I found that it will be exclusive for air. So argon atmosphere, we have to open this one. But I tried little bit, I tried in air environment, and I found after certain time, within 5 minutes, I found some color changes. When these WCl6 we put in ethanol in air environment, I found after 5 minutes, I found some dark color solution. And I took this one and I found this is tungsten hydroxide. Obviously, after XRD, we can understand this one, but we found this sample, this powder, and this one. Then we just heat these samples we just heat this sample in air environment for 2 hours, and we found that is tungsten oxide. And I just think that why I will try with this one. I will try with the current methods. So we just hydrothermal method, solvothermal method, we just for different duration. So the first one when we did, like you can see now how interesting morphology got when we just put that WCl6 in ethanol. We found that some stacked nanoplates. We found the nanoplates are well stacked, and those nanoplates are in square shape. And when we heat these samples, then we found the morphology remains same. However, we found some gaps between those nanoplates. Why these gaps will occur? Because when we heat these samples in the air environment, then water molecule comes out. So when water molecule switch comes out, so gap formation will occur. So we found we should prepare two samples. We just prepared, one is W3H2 and another is W3. Then we tested the samples for hydrogen evolution. You can see from the first one that current density with this our sample we tested, we compare with platinum. You can see that our sample, the over potential, you can see the over potential or current density is comparable with platinum. So we can claim that we can also replace platinum, we can by using this tungsten oxide. And also we found that top L slope is also small, like little bit higher compared to platinums. Then we tested several ways. Then we tested like electrochemical surface area, we calculated surface activity, we calculated all the samples, and what is the reason behind it. For other samples, why the one particular sample shows higher catalytic activity. To understand this also, we have to understand the electrochemical surface area where it is higher, the surface activity where it was higher, where surface area is higher, and also charge transfer resistance or electron transfer resistance is higher. So for that, this one is an electrochemical or impedance spectroscopy. We found that the highest activity samples has lower charge transfer resistance. In particular, this one, the semicircle shows the charge transfer resistance. And lower charge transfer resistance means higher activity or higher electron transport will occur. So in particular, we found that the highest activity sample shows lower charge transfer resistance. And for practical application, it is highly important to measure those hydrogen quantitatively. So for that, we prepared a homemade chamber and on that homemade, on the closed chamber, we just, we used some, like we closed the chamber, then we did that reaction generally in a 3 electrode cell. We put our catalyst, we put our catalyst, then particular current we just apply on that by chronoamperometry technique. And whatever the hydrogen generated on that in that vessel, from the syringe we take that hydrogens and we measure by gas chromatography. And we can see that at 10 hours, when we perform this experiment for 10 hours, we able to generate hydrogen 20 millimole per centimeter square. We also found that this shows much higher compared to previous reports. And for more practical application, we found some nature papers, they generally use seawater to generate hydrogen. So that time I think, why not distilled water we will try. So I also tried this one for distilled water. And we found also distilled water also it was showing little bit, it also showing, but the performance was very less, but we also found that our material can be used in distilled water also for the water splitting reactions. And you can see that this is the table where we like the uses like the TOEFL slope, we calculate the TOEFL slope, we calculate the over potential, and you can see now it was comparable with the platinum. For platinum it was 29, in our case we got some 38.53. So those materials can be synthesized at room temperature, can be used to produce hydrogen generation. So recently we published also one paper. Very recently it was published also for the generation of hydrogen also we prepared by this W3 based material we prepared. That this one also we prepared at room temperature. We prepared some several different phases like W3H2, W3-2H2, W3-0.33H2. And we found that W3-2H2 shows higher activity compared to these phases due to the smaller sizes, and also we given several reasons behind it. Here we found also oxygen vacancies plays important role, and we also found that it was highly comparable with platinum. Here we did bifunctional application, not only HER, but also we performed your fuel cell application, that is ORR, energy conversion, energy oxygen reduction reaction. So now photoelectrochemical water spreading application. So in this case, same as electrochemical application, we perform the generation of hydrogen. Here also our aim is to produce hydrogen or oxygen, but in the presence of light. So what will be the beneficial effect we will observe from this experiment? So when we will use some light, then what will happen? Then over potential will decreases. Means our performance will again enhanced by using the light. So the whatever we prepared, that sample was nanoplates. We just did that solvothermal reaction of those nanoplates. You can see now when we did some different duration of reaction, then these nanoplates are converted to nanowires. For smaller duration, you can see that here dissolution and recrystallization occurs. Like those nanoplates are dissolved, and then some nanowires formation occurs. You can see for during 3 hours, some nanowires was grown. And after 6 hours, you can see those plates are there, but all are converted to nanowires. But when we did the 12-hour experiment, you can see only nanowires are there, there is no plate. The same thing also reflected in our X-ray diffraction pattern. If you can say that W3, that one is W3H2, but in this case, B, C, D, you can see when we increase the time, the growth plane, this growth plane changes, this growth orientation also changes. So from that, we can say that this growth orientation due to the plate, but this orientation is due to that nanowires, which was also observed, that means 200 plane, which was also observed in our TM analysis. So for better understanding this APS images, we did also TM analysis. You can see when this was nanoplate, the growth orientation was 111 plane. But when it was converted to, this means nanoplates, means that is a two-dimensional structures. And when it was converted to one-dimensional structures, then you can see the growth orientation changes to 200, which was also reflected in our X-ray diffraction patterns. And we found that 1D structures shows much higher activity compared to 2D structures. Since nanowires means the electron transfer or electric transfer becomes much higher compared to the nanoplates, means nanoplates are stacked in nature. So, and also we found the surface area also we found in case of nanowires, it was higher compared to the pristine, compared to the nanoplates. And we use those materials for photoelectrochemical. You can see from this one, when we expose light turn on and off. When we light turn on, then suddenly the activity was increases, the current density was increases. When light off, it was again come to the normal positions. Means this material is highly photoactive, it's light active. So we use visible light here, and we found that you can see now onset potentials decreases. This onset potentials decreases. In case of nanowire, it was smallest, means activity also higher. In this case, 3 point something. Also due to higher surface area, due to 1D growth, we found that that the hydrogen generation higher in case of the nanowires compared to the nanoplates. And this photocurrent, when we measure, we found that nanowires shows 21 times higher compared to these nanoplates. So to understand about the mechanisms, about that what is this is an N-type or P-type, so we calculated the flat potentials, we found all are positive slopes, so means this is an N-type materials, and also we calculated donor densities and flat potential. We also found this is higher in case of the nanowires compared to the nanoplates. And also charge transfer resistance we calculate, we also found the lower charge transfer resistance for in case of nanowires. So from those we can conclude that nanowires is higher activity or higher current density, higher photocurrents compared to nanoplates due to the reason of higher donor density, higher flat potentials, lower charge transfer resistance, higher surface area. And also here, not only that, here also we found that growth orientation plays an important role. Means 1D growth shows higher activity compared to 2D growth. Similarly, we also prepared several other nanostructures using microwave assisted methods. When we use some microwave assisted methods to prepare this material, you can see that those nanoplates can be converted to interesting nanoflowers. So if we, like previously, we prepare the materials using solvothermal methods. The solvothermal or hydrothermal method, that is nothing but pressure cooker. We can get higher crystallinity at lower temperature. But in case of microwave method, we just use microwave power, we just use some power. The importance of this microwave method, here we can prepare a material in a very short duration. I think this sample, previously the same sample we prepared in solvothermal method 12 hours, here we can get in 10 minutes. So the 12-hour sample can be prepared in few minutes, in 10 minutes. So that is the beauty of microwave. So here also we understand that from that in case of flowers in consisting with nanowires shows higher activity compared to the nanoplates. So now energy storage application. Generally, we are interested to generate energy by using renewable resources. If we can see the renewable resources, two things will come into the picture like sun and wind. If we can think about the sun, which shine only in daytime, not in night time. Though we are using the renewable resources to generate energy, at the same time, we are also trying to developing some hybrid cars, hybrid vehicles with low emission of carbon dioxide. If we can see about the renewable resources like sun, which do not shine at night time, wind, which do not blow on our demand. However, whatever the car we want to develop, that we will drive on our demand. So from this, it is suggests that an energy storage system is required. If we can store those energies, then only we can drive our car. So a storage system is required. If you can see the storage systems, mainly there are two types of storage systems are there. One is battery, another is supercapacitors. If we can compare between batteries and supercapacitors, generally battery has slow charge discharge, large volume, short life. But in supercapacitors, it is fast charge discharge. Generally, we are using mobile phones, we are using lithium-ion batteries. It takes to charge around 1 hour, 2 hours. But here we can charge in supercapacitor, we can charge this in 10 seconds. So first charge but discharge also fast. First discharge. small volume, long life. And but the importance is in battery that energy density is little bit higher compared to supercapacitor. So it is, but power density of a supercapacitor is very high, but energy density is less compared to batteries. So our aim is to implement the materials, to design the materials which can show higher energy density. And these supercapacitors, mainly supercapacitors, can be divided broadly into two types. One is called electrochemical double layer capacitor, another is called pseudo capacitor. Electrochemical double layer capacitor means here the storage mechanism will be the absorption of the ions on the electrode surface. Generally, carbon based materials are used for electrochemical double layer capacitors. So since only absorption occurs on the electrodes, so on the electrode and electrolyte interface, so the specific capacitance becomes very low. On the other hand, pseudo-capacitors means charge storage occurs due to the reversible reactions or pseudo reactions will occur. So in this case, redox reactions occurs. So in this case, we able to get high specific capacitance. Generally, transition metal oxides, phosphides, sulfides are used for these pseudo capacitors. So if we can combine these two pseudo capacitors and EDLCs, then means we can get a hybrid capacitors. So if you can able to prepare some hybrid capacitors or materials by combining these two, both EDLCs and pseudo behavior will be there, then we can able to achieve higher specific capacitance. So our aim is to able to achieve higher energy density and higher specific capacitance. So in this one, we prepared graphene W3 composites. So we have taken one, we prepared one only graphene, we prepared only tungsten oxide, then we combine several percentage of graphene we combine to prepare the composite. Then we want to know the optimum graphene amount required for this composite for the performances. So you can see now 3 samples we prepared, not only 3, we prepared 10 samples, but here we just shows the highest percentage of graphene when we prepare the best sample. Means 10% of graphene and W3. So you can see now this is only graphene, only W3, this is the composite. But from the XRD pattern, we did not able to get any peaks of the graphene at around 26. We can see that this peak was overlapped on this peak with this peak. But we can see from these first 3 peaks, we can see that the growth orientation changes due to the interaction of graphene. And for better understanding, we did Raman spectroscopy. From that Raman spectroscopy, you can see that in the graphene, only normal graphene, we found 2 big D band and G band here. In W3, there is no D band, G band, but in the composite, you can see very less amount. You can see that the peak observed. So where you can confirm that the composite occurs. And we check the surface area of those samples. You can see when we prepared a composite, the surface area was enhanced much higher, like 186 in case of only W3, 132, only graphene 60, but in the composite 186. Why? What's the reason behind it? Why in the composite we got higher specific surface area? Because in case normally graphene, these carbon-based materials, they are layer structures. So since we are preparing these materials, so maybe there are several layers will be there. So when we prepare a composite, that W3 interact with this graphene on that layer structures, so it will interact, so it will enter between that 2 layers. So when that W3 nanowires enter to the layers, so gap formation will occur. So when gap formation will occur, then the surface obviously void formation, obviously surface area will increases. And for better understanding, we did the FESM and TM analysis where you can see that only nanowires are there, and in the composite you can see that on that graphene sheet nicely these nanowires are decorated throughout that graphene layer surface. Then we studied the electrochemical performance of those samples. We found a certain percentage of when we use the certain percentage of graphene, then we found like 10% of graphene, not 15. We used also 15 also. We found the electrochemical area, the CP area was higher compared to other samples. So since higher the CP area means it suggests that it should have higher specific capacitance. And also we measure the specific capacitance from that CP curve. We measure the specific capacitance, and we found that certain percent we found that we did some all the samples. We found that highest is 10% graphene. When more amount of graphene, more than 10%, then again we found that the area was decreases. So from that we understand that particular optimum is 10% graphene in W3. If higher amount of graphene will be there, then performance again decreases. And also we observed that specific capacitance, we also observe for certain cases, we also observe on that particular composite is higher compared to the other one. And when we increase the current, increase the standard, then specific capacitance decreases. That is because it get less time, because when we do this reaction, since it get less time, so S plus ion cannot interact with the is ions on the electrode electrolyte interface. So at higher standard we will get less specific capacitance. Similarly, you can see that so the charge discharge plot for pure graphene, you can see this is not clearly visible, but it was like linear shape, symmetric, since there is no redox reaction occurs. But in case of the composites, there is not linearity, non-linearity observed, means the pseudo reaction or reversible reactions occurs. And also we observed at higher specific, also at lower current density we got higher specific capacitance, at higher current density we got lower specific capacitance.
Hello. Sir.
Yes.
We'll take questions, sir.
Yes, it's just 2 minutes, I will finish.
Okay, sir. Thank you, sir.
Also, we found that composite shows higher specific capacitance and lower charge transfer resistance. Then, for practical applications, we prepare several cycles, and also we found these materials is highly stable. Then we prepare some device. We design some asymmetric superstar. Real device we prepare. We design some real devices. You can see now the device. We prepare this device, and we just charge this one for 10 seconds. And this LED, this had I think 10 or 12 LEDs. We close. This LEDs can glow up to 6 minutes. We just charge this for 10 seconds. But this performance was not so high, which we can say industrially we can produce this one. But we are taking several attempts. We are now also emphasizing on this to develop some new materials where we can able to achieve some high specific capacitance with high energy density. Here another materials we also prepared for this one: gold, iron, manganese composite. Here also we observed also we can able to achieve, but the specific capacitance or energy density is little lower. So still yet we are trying to design different metals. So here also another materials, we also designing some different materials, and we are trying to achieve high specific capacitance as well as high energy density. So in a conclusion, I can say in conclusion I can say that the materials which can be prepared by either in room temperature or by hydrothermal or solvothermal methods can be used for several applications, or in energy applications like in hydrogen generations, or in energy storage applications as supercapacitors. Also we can use those materials for gas sensing applications, and also environmental remediation in terms of the degradation of several dyes.